Okay, now we'll start. So last time we said that we proved that projective varieties are complete. So this means in particular that if x is projective, and E from x to y is a morphism to another variety, then it follows that the image P of x in y is closed. And but we had also seen that there are some other crazy properties, namely corollary. If x is projective, y is affine, then any morphism phi from x to y is constant. So maps the whole of x to one point. In particular, if you have a regular function on a projective variety, it is a constant function. Now, one of the things, so this is actually used quite often to somehow make new projective varieties out of old ones. So if you have a projective variety, you have some morphism to some projective space, then the image will again be a projective variety. It will first be closed as the image of a map from a projective variety, and second, it will be irreducible, because if you start with something irreducible, then the image will be irreducible. So this is how one, in this way, one can get new varieties from old ones. And so, if x is projective, phi x to say the n is a morphism, and then phi of x, the n is a closed subvariety, so it is a projective variety. So I want to look at one example for that, because I will also use it in the next chapter, which is the Leone embedding. So we choose some numbers n and d bigger than 0, and we put large n to equal to n plus d, choose whatever n or d, minus 1. So we denote mi for I from 1 from 0. So n all the monomials of degree b in x0 until xn. So you can easily see that the number of these monomials will be n plus 1, and so this will be this. And so we define the Leone embedding say nu n, nu d from Pn to the large n is defined by, it's actually a polynomial map, so I can write it as m0 until Mn. So just every point, so A0 to An is sent to M0 of A0 to N and so on. So where these are all the monomials of degree D. So we map the N into a rather large projective space. And this is a morphism. These are all homogeneous polynomials of the same degree, so it would be a polynomial map. What we need is that they don't have a common zero on Pn, because among the Mi are x0 to the d until xn to the d, and no, on Pn, x0 until xn don't have a common zero, so also these don't have a common zero. So there are already n plus 1 elements among these which don't have a common zero, so therefore they don't all have a common zero. No? So the condition for something given by homogeneous like this to be a morphism was that these are homogeneous polynomials of the same degree with no common zeros. So this is what defines a polynomial map. Morphisms are more general. We can define it by rational functions here and so on. Remember the definition. So this is a morphism. And now, I denote BD, the image, so this is called the Leone variety. So after an Italian partition Leonese. And so this, I mean, in some sense, we will see in a moment that this map is actually an isomorphism. So after isomorphism, this VD is just Pn. But still, these Leonese varieties play an important role because often they are counterexamples to things that one might think are true. You know, how a subvariety can lie in projective space. So often there are some kind of things which are in general true, except that the Veronese would be a counterexample. So in that sense, they are important somehow. But now the claim is that this thing is an isomorphism. So, as I said, this VD is by our theorems is a closed subvariety of Pn, and so this makes sense. We can look at we could try to look at the inverse map. Let me first maybe I want to briefly say, so I can have a little question of the homogeneous ideal of VD. So maybe first to have some notation so that we can, because it's a bit confusing. So here we have the monomials in x1 to xn, and they map to here, so the coordinates here somehow corresponds to the monomials here. So we want to somehow indicate that they correspond to them, but without confusing the issue too much. So maybe I say, so note, I have to decide, I want to decide so for monomial ZMI for the corresponding coordinate on P large M. That's actually a bit stupid. Well, anyway, so I write M. So in principle, I could just have called it ZI versus I, but later, actually, I want to use what corresponds to what. So ZM for the corresponding coordinate on Pm. No, here, this is just counting them. There are as many coordinates on Pn, namely n plus 1, as there are such monomials, and so we have this correspondence, and by the map one somehow sends a point here to the corresponding coordinate, so in this way. So then, if I look at the ideal of this VD, this will always contain the following. This contains, say, Z M I times V M J minus Z M K times Z M L whenever M I times M J MK times ML. This is geo, no? Because on the image, a point in the image is just MI, so just the coordinates are just the different MIs applied to the coordinates of the point P. So here it really just says that MI of P times MJ of P is equal to this times this. This is the condition here, and this is certainly just true if these polynomials are the same. So this on the image, this will hold. So these clearly lie in the ideal, so by definition. I think one should be able to prove, I mean as an exercise, we don't need it because we know that it's closed, but you as an exercise, you could try to prove that the ideal of the Veronese variety is the ideal generated by all these. Okay, there are very many equations. And, okay, so but once we do this, so now we can define the inverse morphism to VD. So we define inverse morphism to VD. So this I just take as, maybe I call it mu D from VD. So Pn, and here I just take, for instance, I can write it in several ways. I now write in terms of rational functions, so 1, comma, Z corresponding to x0 to the d minus 1 x1 until Z corresponding to x0 to the d minus 1 xn, divided each of them by just Z to the x0 to the d. Oh, where is this? And I claim that this is also equal to the same, where instead of x0 I choose any other xi. Z to the xi to the d. Okay. So this, so once these are equal, you can see that this is everywhere defined. So that this defines indeed the morphism. and you can check immediately that it's inverse to the morphism given here, because somehow you can recover, if you start with a point, you can recover the coordinates of the point. And if you are able to, as I said, if you're able to write it like this, these are the same map. And you have to use this relation to show that these two are the same as rational functions. So that you can apply these relations to replace maybe some of these zi's by some others, and then apply the multiply by some rational function to show that they are the same, and then it follows. And so with this, this is the exercise. Okay. So given this, we know that this is in some sense just a crazy way of embedding Pn into some bigger projective space. But we actually are going to use it because it has some special properties which are useful. But first, let me look at the simplest example. Namely, so the simplest example is mu d from P1 to PD, and so according to our thing, we send point AB to A to the D, A to the D minus 1 D, and so on until B to the D. And the image is called a rational normal curve. So in this particular case, Leone variety is called a rational curve. It's called rational normal curve. So this, I mean, just to say it, you don't have to actually understand it. So this is the, so if you would call the degree of a curve, in some sense, well, how many, if you take a hyperplane and how many, in general hyperplane, and how many points it will intersect it, and you will find the degree is d. And so this is actually these are, so up to projective linear transformations, these are the only degree d curves in PD which do not lie in a hyperplane. So in that sense, it's also some kind of counterexample to something. So they are always somehow a bit special. And now I want to, however, use this for something. Maybe I want to first, I don't know whether I actually introduced this, but we have now introduced isomorphism and so on. So normally, if two things are isomorphic, you want to somehow see them as essentially the same. So therefore, if a variety is isomorphic to a subvariety of a fine space, we want to call it a fine. So which differs from our original definition. Subvariety of an of some an, it is called a fine variety. Obviously, okay. So now I have this corollary. So let X in N be a projective variety. We take F, a homogeneous polynomial, in the coordinates there of degree D. And first, X without the zero set of F is an affine variety. So it's isomorphic to a closed subvariety of some affine space. And the second statement follows from this by what we know. If X was our projective variety, is not a point, then X intersected with the zero set of F is not the empty set. So every if you have a projective variety and a hypersurface of some degree d, it will always have non-empty intersection, unless this variety was a point. Obviously, you can choose a point which doesn't lie on the hyperplane. This will be important for us when we want to study dimension of varieties.
Excuse me, here ZF it means as a subvariety of Bn, as an algebraic set in Bn, or
What?
ZF.
Yeah, in Pn. Yeah, we are in Pn. Yeah, no, it plays in Pn. I mean, the fact that I will use the word affine variety does not mean we are. No, this just means this thing is isomorphic to a closed subvariety of An, but it's of some An. It actually turns out of some much bigger An. And but we are always in projective space here. This is the, if you wish, it's this. But I thought here was no reason for confusion. Okay. So if the degree is equal to 1, then we are looking at the, so we prove 1. If the degree is equal to 1, we look at the complement of a hyperplane, and we can use a projective linear transformation to move that to the hyperplane at infinity. So then by projective transformation or projective change of coordinates, which defines an isomorphism of the N with itself, we can assume that the zero set of F is just the zero set of X0. And so then X without zero set of X0 is just X intersected An, and so this is an affine variety. No, because X itself was closed, so that is a closed subset of An, and so it is an affine variety. Okay, so now that was kind of a trivial thing, but we have the general case with F is higher degree we want to reduce to this case by using the Veronese embedding. So now, so if F has degree b bigger than 1, then via the Veronese map, we have that X minus the zero set of F is isomorphic to its image under the Veronese map. So that means to the image, the Veronese embedding of X minus no, because this is projective, so this will close this. So we you know, it's all up to isomorphism. We want to show that this thing will define variety. So, so what is this? So if I take nu d of x, or maybe I just talk first about this. Is what? So this is equal to the set of all points which lie in the image of the Leonese, such that if I take some, so if I write now f, so write, maybe write it here, so write f equal to sum I equals 0 to, what was it, n? No, that was I think the mention of the mi of these monomials. So this means sum ai mi applied to p. So where the ai is some elements in k. So an arbitrary polynomial of degree n of degree d can be written as a linear combination of these monomials. And so we just apply this to p. This is equal to 0. Okay. Now, however, this is the same. So these mi, so the coordinates correspond. So the Veronese map will map this thing via the mi. So this means if I take the points inside the image, then the condition for this will be that some ai, the coordinate corresponding to this of the point is equal to 0. So this means this is the sum ai, ai, I had called this z mi of q is equal to 0. So this is, in other words, equal to vd of, so vd intersected the 0 set of sum ai z mi, which is now a polynomial of degree 1. So thus x without c of f is isomorphic to d of x minus the 0 set of sum I, ai, z of mi. So it's the complement of the linear form, of the 0 set of linear form, so it is a fund. Oh, by the degree 1. So it's kind of, so you can, by this embedding, you can reduce the 0 set of polynomials of any degree to the 0 set of polynomials of degree 1. So to hyperplanes. At the price that you have to embed your thing into a very big projective space. But anyway, if we are interested just in knowing whether this is fine. And so the second statement is then clear. Now I wiped it out, but I have remembered it. So if x intersected the 0 set of f is empty, then x is equal to x minus the 0 set of f. So x is projective, x minus the 0 set of f, which is also x, is affine, so x is affine and projective. So by what we know, it follows that x is a point. Because points are the only varieties which are both affine and projective. Okay, so this was this. Took a bit longer than I thought, but anyway. So now I wanted to briefly, I mean, we will not really use it, but I wanted to briefly return to rational maps and talk about birational maps, so which is, as you know, a rational map is a morphism which is not defined everywhere, just on an empty open subset. So a birational map is a rational map which is an inverse. And so if you have, in this case you call the two varieties birational or birationally equivalent, and this will imply that they contain open subsets which are isomorphic. And for many purposes, this is a kind of a coarser notion than isomorphism, but it's still a meaningful one. And we also can see that this can be, being birational is equivalent to having isomorphic, how you call it, rational function fields. Okay, so all these things I want to very briefly explain, but I will be a bit sketchy because we're not going to actually use it. I start slowly, but then show birational maps. So remember, we have rational maps. Phi from x to y between defined objective or quasi-projective varieties. So the first thing that we want to know, would like to compose them. No? Morphisms you can compose, so we would like to compose them. So assume we have a rational map like this, and C from Y to Z, both rational maps. So is there the composition? So I want to define composition. So the composition.
Can we intersect with open sets on Y?
Yeah, there is some such. I mean, that is somehow the problem, but let me somehow say it. The composition is not always defined, not necessarily defined. As rational map, because somehow what it could be that if I take the image of phi, by which I mean the image of the part where phi is defined, this will be some open subset of y. Then, this is some subset of y. It doesn't have to be open. It could be anything. It could be very small. So this thing, intersected with the place where this map is defined could be empty. They could not have anything to do each other. So with the domain of psi could be empty. And obviously, if we have this, so we map the points from here somewhere, but all the points where we map it, this map is not defined, so there's no way how the composition could be defined anywhere. No? So we have somehow this is x, this is y, this is z. So here x maps this thing into some small subset like this, and y, obviously is defined on some I mean, so this is phi, and then the domain of phi somehow, well, I just write it like this. Obviously, it's a dense open subset, but it looks like this. It doesn't intersect this, so this would be psi. Then there's no way you can compose them, because no point, I mean, no point from here actually makes all the way from here to here.
But by definition, we have that there is an isomorphism between open sets in X and Y, right?
Well, that I still have to show you.
I mean, just by being a rational map, we know.
No, they're not an isomorphism. It's defined.
A morphism, sorry.
A morphism on an open set, yeah. So in some sense, this picture is misleading. So it will be. So I don't have colors, no. So this thing will somehow assume this whole thing is mapped to a point. Could happen, or anyway to something smaller dimensional. And this thing is defined, you know, on the whole thing minus this. And the point lies on it, then obviously the composition is not defined. I mean, where it is defined is an open set, so in that sense this picture I made before is nonsense. But anyway, okay, so we have to make first a remedy for this, and this we do by talking about dominant rational maps. Dominant means that the image contains an open subset. And such things can be defined. So, actually maybe, well, I could say it's an open subset, or I just say that it stands. A rational map phi from X to Y is called dominant if I take the image. So the image is always the image of where it's defined, is dense in Y. Obviously, if it's dense in Y, then any open subset in Y must intersect. So assume that phi from X to Y is dominant rational map. And say psi from Y to Z is just a rational map. Then we can define the composition. So the composition C composed with phi is given as follows. So obviously, so it's just actually we get that, so on the open subset the domain of phi intersected with the inverse image of the domain of psi, which is just given by the composition. So it is just phi composed with psi of P is just psi of P. And we can see that this is a rational map. You know, so for instance, if we for simplicity just assume that phi, that x and y, x, y, and z are all in some affine space, doesn't make a big, so if say y is in En and z is in M are some subvarieties, then we know that the phi can be written as f1 to fn. Is that right? Yes. Where the fi are rational functions on x. Psi can be written as g1 to gm, where the gi are rational functions on Y. No, this is how we have defined morphisms to, rational maps. And so then obviously phi psi composed with phi will just be given by g1 of f1 to fn until gm of f1 to fn. So we have just replaced the coordinates by these functions, and these can easily be seen to be rational functions. Gi of f1 is an element in X. As you can see,
I'm just wondering, is it we are requiring that phi of domain of phi is dense or just only dense, or
dense is enough.
not necessarily open?
No, that so one, I think, you could require, which might or might not be equivalent, that it contains an open subset. But it certainly, you don't want to require that the image is open. Mm-hmm. It's not necessarily true that if you start with an open subset, the image will be open. It can be, it can be something, can be neither open nor closed. But it's really, we don't have to worry about this. It's, for this definition, it's enough that the image is dense. I think it would then follow, if you're more carefully, that it contains an open subset, but we don't care about it. So I just wanted to say, where is it? So if you write, for instance, Gi equal to L, so the class of Li divided by the class of Hi, where these Li and Hi are monomials, and then y x1 to xm, I think. Let me see. I think no, it's okay. So where this class means the class in the coordinate ring, then clearly we have the Gi of f1 to fn is just Li of f1 to fn divided by Hi of f1 to fn. And the condition that we have here, that these are non-empty, will precisely that this so what we need for this to be rational function is that this is not identically 0. It's not 0 because we have that the domain of the Gi intersecting with the image is non-empty, so this cannot be everywhere 0. Okay, so that's the Gi. So therefore, C composed with phi is a rational map. Okay. So note, and now I can tell you what a birational map is. Maybe I first want to say one more thing. So in particular, we know that rational functions are just rational maps to A1. So therefore, we can also, so the pullback of a rational function is just a composition with a morphism. And so we can define the pullback of rational functions via dominant rational maps. So definition. the rational function. I should say, so here, before I finish this, here I've done it under the assumption that these lie in a fine space. So, but there's no real difference. If we're in projective space, we have instead to work with homogeneous polynomials, and maybe up to multiplying by some, but the arguments will be more or less precisely the same to show that if you start with a rational map, you get a rational map by composition. It's just a little bit more complicated, but it's otherwise the same argument.
I have a question here. So, do we assume that it is dense to guarantee that this intersection is not empty, right?
Yeah, basically.
But why if the intersection of two dense sets cannot be empty?
Well, it's not two dense sets. The domain is an open set.
Yes. A
non-empty open set. And so if the set is dense, then the intersection with any non-empty open set is non-empty. Okay? So, it's true, one couldn't, it wouldn't be enough to say we have two dense sets, but we have one dense set and one open set, and so the intersection is not empty. But as I said, most likely one can show that under this assumption the image contains an open subset, and so then the probable term doesn't, but it's easier. So a rational function f y is just, we know that, a rational map. An f from x to a1. So thus we can define the pullback. So for a dominant rational map, so this was y. Cp from x to y, we have the pullback phi star from ky to kx, which no pullback just means composition with phi, so f is sent to f composed with phi. And if this was a rational map and that was a dominant rational map, this is also a rational map from now x to a1, so a rational function. So we can do this, and it's clear clearly phi star from ay to kx. So this is a now map is a field homomorphism, and in fact a k homomorphism, a small k homomorphism of fields. No, because it's compatible with addition, multiplication, division, and it's, if you multiply by a constant, you will get the same. So this kx is some very big field extension of our field we had in the beginning, and this is like we had in Galois theory, only it's a bit more, our fields are a little bit bigger here.
But this is out of infinite extensions, right?
Yeah, well, so we'll find out. I will not use that way, but these are normally, so kx will be transcendent, so will be an infinite degree extension, and it will have a certain transcendence degree, so there will be, and one way how one could define the dimension of x would be equal to the transcendence degree of this field extension, although this is not the route that we will take. Okay, so these are normally, so unless x itself is a point, this will have infinite degree. But yeah, as you can also easily, do. I mean, one can see that if one, well, I don't know how easy it is, but anyway. So what do you want to say? So this is the and now I wanted to say, finishing. The dominant version map phi from x to y is called birational map if it has an inverse. So if there is another, so a dominant versional map, psi from y to x, with you know, psi composed with phi is the, what is it, the identity on x, and phi composed with psi is equal to the identity on y. So that means that on the open subset where, you know, on some open subsets you can compose these two, and they're the identity, but that means as rational maps, it's actually the morphism identity on x and the identity on y, because the rational map is determined by what happens on an open subset. Okay, so if a rational map has an inverse, then it's a birational map, and in this case, we say that x and y are called something.
But how is identity on x and phi itself is not defined on all of us?
Well, so yes, but you see, a rational map is always defined on the largest set on which you can define it. So if you take this if you take this composition, a priori it's defined on some smaller set. No, the domain of phi intersected the inverse, so the inverse image of the domain of psi, which is some open subset. And on this open subset, it is the identity on x. And then, however, that means as a rational map, a rational map is this equivalence class or whatever, it turns out this thing is defined everywhere because it's the identity. And so, as a rational map, they're equal. The fact that the way of writing it like this is not everywhere defined doesn't, so you cannot everywhere, this is not everywhere defined, this is not everywhere defined, but still this composition is everywhere defined because you always define it on the biggest set on which you can. But obviously not in this way. I mean, it's just a rational map by definition is just given by an n tuple of rational functions, and will be defined on the biggest open set where this makes sense. And if the thing is the identity, obviously the biggest open set where it makes sense is everywhere. But it's a bit confusing, I must admit, because you say that two things are equal, and this one looks like it's not everywhere defined, but in some sense this composition is everywhere defined, even though the pieces aren't. Okay, just in this case, x and y are called. You often say birationally equivalent, but I just say birational. Okay. And as I said, it's some kind of coarser form of isomorphism. So if x is birational, so say for Pn, we say x is rational. So we had this rational normal curve before, that is one such case. Or anyway. So, and now I want to, so one stupid thing for a remark, obviously, any variety will be birational to any open subset, a non-empty open subset. So let X be a variety. U in X non-empty open subset. And then maybe I just denote it like this, not with 2 but just with 1. So then X is birational to U. No, and I mean this is clear, you can just take, so because the identity of X of U is a rational map from X to U, and its inverse is the identity of U, which is a morphism from U to X, and these are inverse to each other. Okay, so this is just this, and this just is, you know, the identity on X here is, you know, it happens to be defined as a map to U, it just is defined on U, which is our open subset of X, so it's a morph. So it's kind of stupid. So in coordinates, you can also write it, for instance, as a, you know, you can certainly write down the identity as a rational, in terms of rational function. So this is kind of, but okay. So we see that this is the most, but in some sense, I now want to say that up to, that in some sense, this is almost all that a rational map is. So up to isomorphism, two things are birational if they have isomorphic open subsets. So let me formulate this as a theorem. The following are equivalent. First, no, which one? Anyway, Kx is isomorphic to Ky, known as fields over K. Second would be X and Y are rational. And the third would be they are non-empty open subsets say U in X and V in Y such that U is isomorphic to Y. Okay, so this is the. I will prove it, but not in all detail. So the easy things I give a complete proof. The things which would require some work, I maybe cheat a little bit, or at least say leave some part as exercise, because it would take a certain amount of work to kind of cross all the T's. So so what do I want? Let me start. So for instance, I start with 2, so goes to 1. I have to show that all these many things are equivalent. So this is not so. So let phi from X to Y, C from Y X, the inverse dominant rational maps. So that means if I take P composed with C, this is the identity on X, interpret psi composed with V. Is it precisely wrong? Yes, identity on Y, and this is the identity on X. So, so now I can, obviously I can compose the pullback, and if I compose twice the pullback, it will give me the identity. So it follows that psi star, or if I just say psi star composed with phi star is the identity on ky, no, just as the pullback by the identity, and phi star composed with psi star is the identity on kx. So that means, say, phi star from kx, ky to kx is an isomorphism. No, whose inverse is psi star. So this is an easy one. So I first do the easy ones, so I can also do 3 to 2. So we assume that there are such non-empty open subsets. We want to show they are birational. That's in some sense trivial. So we have birational maps. I mean dominant birational maps. X maps to U, as U is an open subset, maps with this isomorphism, whatever it was called, to V, and this is actually a morphism, but anyway it's a rational to Y. So this is an isomorphism, this is a birational map, this is a birational map, which happens to be a morphism, but that doesn't matter. Anyway, and they are all dominant, so it follows that this composition is also birational map. So does X, Y is a birational map. I mean, obviously I can also tell you what the inverse is. The inverse is just putting it together. Okay. So let me see. Yeah. Maybe I can try 1 to 2. So we can assume X is a subvariety of AN and Y is a subvariety of AN. Why is that? If we take, X somehow lies in some, maybe it anyway lies in a finite projective space. Assume it lies in projective N space, then we can intersect it with so we can take a complement of some hyperplane, so that it now, which gives us an open non-empty open subset of X, which is therefore birational to the original X. So by kind of taking the intersection with the N, making sure obviously that it doesn't lie on the hyperplane infinity by some transformation, we can assume that X is in AN in the same way that Y is in AN. So we can reduce ourselves to this case. And then I just give the idea. So we have our map, call it. So what do we have? we wanted to go from 1 to 2, so we assume that, say, whatever, large phi from ky to kx is an isomorphism. So that we want to show. So then, so let y1. So then we do something very similar as what we did when we started with the morphisms, when we talked about polynomial maps, and that the polynomial map gives us a homomorphism between the coordinate rings. We do basically the same thing here, homomorphism between the coordinate and ring and vice versa. So we have to take y1 to ym, here, the coordinate functions on em, so that means the restrictions of the coordinates to y, and we put fi to be psi of yi. So these are some element in kx. And so then, if I take f1 to fm, this defines me a rational map from x. If I already it's a rational map to em, and you have to check it actually maps into y. And I claim that because this was an isomorphism, it actually is an isomorphism. It's a rational map. And in fact, it is an isomorphism because we can see what its inverse should be. So if we put instead, so I take x1 to xn, the coordinate functions on this a on x. So then we can put gi to be equal to phi to the minus 1 of xi, which is an element in ky. No? And then, so we get another rational map g1 to gn from y to x, and then one has to check that these are inverse to each other. Oops, maybe not. So these are inverse. And the last thing that I wanted to show is maybe from 2 to 3. I don't know whether that's all the logic, so let phi from x to y and psi from y to x be bidirectional maps. So this is a rational map. I mean, a dominant rational map, bidirectional map, and psi from y to x is rational inverse. So I can put u equal to the domain of phi intersected with the inverse of the domain of psi. Okay, so these are all the points which lie in the domain of phi and which are mapped into the domain of psi. This will still be is intersect. So this is an open. This is the inverse image of an open subset. This is also open. So this is open in X. And it would be the same thing the other way around. Domain of psi intersected the inverse image of psi of the domain of. And then the exercise is to show that, I mean, you can see directly, if you think for a moment, that U is mapped into V and V is mapped into U. And in fact, you can check that this defines an isomorphism between the two of them. Obviously, its inverse is still psi. Okay, it's just some stupid tricks with sets. Okay. Good. Well, just to finish this. So anyway, this is as much as I wanted to prove this theorem. So as you see, I was a bit sketchy, but I think the ideas are all pretty clear. I wanted to note that P2, A2, so Pn, En, Pn times Pn are rational. This is obviously because each of them contains some affine space. So obviously Pn is birational to An. And you know, if something is birational to P and it's rational, so that's fine. But also Pn times Pm contains as an open subset this. So Pn times Pm has the open subset. If I identified it this way. Embedded, so sigma, which would be the image under this, intersected with this open subset U00, which is isomorphic to An plus M. So and so it's isomorphic to An plus M, so it's birational to Pn plus M, and so it's also rational. Maybe it would have been better if I said the variety is rational if it's birational to some An. It's a bit simpler. Okay. It's actually not so easy for us to prove that some varieties are not rational. I mean, it's actually very rare for varieties to be rational. It's very special, but to prove that is not so easy. So I mean, if I just I can just say that, for instance, I take the general curve of degree 3, then it will not be rational. So if I take, for instance, the zero set of y squared minus x times x plus 1 times x plus 2, so like that, in P2, in A2, this is not rational. But I don't have the methods now to show you that. I mean, there's no, there's no birational map to, in this case, so this to A1 or P1 or something like that. But no, this is just effect. It requires.
Is it because it is singular at origin?
No, this is not singular.
Origin.
No, we are in A2. This is smooth.
The origin, the partial derivatives are 0.
It doesn't contain the. Did I write something wrong? No, the partial derivatives are not 0 at origin.
Yeah,
What?
I'm
No, I mean, because we don't have a quadratic term here. So this is precisely, if you write something like this, z of y squared minus, so x squared times x plus 1, or something like that, that will be singular, and it will also be rational. In fact, if you have a curve like this of degree 3, which is not singular, then it is not rational. And so it's not rational if and only if it is not singular. Okay, so it's precisely the opposite of what you say. Okay, but this is, we don't have the means to prove that, so I just stated it. Maybe we would have the means if we were willing to work for an hour or so. For such a thing, it's not really worth it. Okay, so now I wanted to start with the next chapter. So this was about these morphisms was a rather long story, but these morphisms are tools for us, so we have to develop and sharpen our tools so that then we can use them. Now I wanted to talk about dimension. And I will just start, there's time for the motivation, and then we really start the next time. So we want to introduce dimension of varieties. So obviously we want, so every variety has a number associated to it, which is the dimension, and somehow it should follow the equation of what dimension is. So one thing that it should have, which we are not going to prove, but which is true, is if you have a non-singular variety over the complex numbers, it is a complex manifold, and the dimension that you will associate to it will be the dimension of it as a complex manifold, like you learned in differential geometry. But okay, that's. But if we, this would be difficult to prove because we never compare these things in our thing. But another thing is that we want to have another few properties. So obviously dimension says us how big the thing is, so in how many directions it somehow extends. And so we want some properties. So first, the dimension of an should be equal to the dimension of Pn, and this really looks like it has dimension n. So that we want. So we want. We will have to make the definition, and then we have to prove this, because our definition is not that we do this. And so the second is, now if you think of it, if you have a subvariety, so a variety is already something irreducible. So if you have a subvariety, you really have some equation which really makes it smaller. So you assume that if you have a subvariety of a variety, so a closed subvariety of a variety, then its dimension must be smaller than the bigger variety. So if x, y are varieties, I mean, obviously, then the dimension of x is strictly smaller than the dimension of y. And you might assume that, for instance, if it's just a zero set of one polynomial, it should go down precisely by 1. But that's for the moment we don't see. Obviously, this only makes sense if we talk about varieties. If x is just an algebraic set, it can have many irreducible components, which all might have the same dimension, and if we, these are still closed subsets, so it might then be, if you have an algebraic set, it contains algebraic subsets of the same dimension. But variety means it's only one piece, and if you want to make something smaller, we really have to cut it smaller. Okay? Then, somehow the dimension is a very coarse property, so it talks about how big this thing is. So if we take an open subset, it should have the same dimension. So that means if x and y are rational, then we want that the dimension of x is equal to the dimension of y. What else? Now, okay, so these are a few properties, and we will want to study the dimension via morphisms. So, if we have a morphism from x to y, we want to use this to compare the dimension of x with that of y. So we expect the following. So if we have the correct definition, we want that the following is true. So if f from x to y is a surjective morphism, but if you have a surjective morphism from x to y, somehow y is smaller than x. So the dimension of y should be smaller than that of x. It should be smaller or equal to that of x. Then we want the dimension of x is bigger or equal to that of y. And now, if in addition all the fibers of the map are finite, so that only finitely many points always go on one point, you would expect the dimensions are the same. No? So, if f from x to y is surjective with finite fibers, so it doesn't contract anything, then we want that the dimension of x is actually equal to the dimension of y. Okay, so we will introduce our dimension. We more or less check that with our definition these properties hold, and then we will prove this. But to do this, we look at certain special morphisms which have the property. So we will want to, in a long time, we will mostly want to use this property. Okay, and we will actually use morphisms which have a slightly stronger property than just having finite fibers, namely so-called finite morphisms. So we want to use finite morphisms which are in particular surjective with finite fibers, but have some additional properties. To show, to study the dimension. We'll start out by showing that if we have a finite morphism, which I have not yet defined to you, but it is, then it preserves the dimension. And then one of our main tools will be the so-called Noether normalization theorem. So after, again I think, after Max Noether, who was, I hope it's correct, who was the father of Emmy Noether. I hope I'm not mixing them up. And who also was an algebraic geometer, and which says that if X is a variety, it follows there exists a finite morphism. So, see, I can assume that X lies in some is an affine variety in some affine space, because I can always replace by an open subset, and it follows there exists a finite morphism. X to an to some n. And by what I just said, n will then be the dimension of x. So this will allow us to kind of reduce our study of dimensions somehow to affine spaces, and so that and so this is part of the program. And I mean, I didn't. Now the next thing that I have to do is to introduce to you finite morphisms. And finite morphisms have to do with finitely generated modules, and so I will want to explain this on Wednesday. Okay, thanks. So.